starship was poised on the edge of the virtual vortex. The captain was nervous, his finger on the button. He looked at the strange image on the screen. He knew deep down he would need some incredible bandwidth to tackle this monster. The hybrid memory cube was feared and revered throughout the galaxy. Okay, just kidding. We all know that the hybrid memory cube isn't really a mysterious villain from a sci-fi series. But that would be pretty cool, right? Yeah, arms 30s torpedoes. Fire! Okay, but HMC technology has enormous potential to help us attack the storage glut, particularly in 400 gig applications. But getting data in and out of the HMC efficiently is a serious challenge, worthy of some serious technology. Hi, I'm Amelia Dalton, host of Chalk Talk. Today my guest is Manish of Altera, and we're going to talk about how we can accelerate system memory bandwidth using Altera FPGAs with the hybrid memory cube. Pew pew! Pew pew pew! Okay, just kidding again. Before we get started, remember to click that link. There you can download a free white paper entitled Addressing Next Generation Memory Requirements with Hybrid Memory Cube Technology. Welcome, Manish. Thank you so much for joining me today.
Hey, thanks a lot, Amelia. It's great to be here.
Okay, before we jump into the details about the hybrid memory cube, let's talk about memory in general, because our appetite for memory bandwidth is going kind of crazy, isn't it?
That is exactly right. If you look at industry trends today, what you'll find, Amelia, is that there is an insatiable need for memory bandwidth. Now, this insatiable need for memory bandwidth, turns out, is coming from a variety of sources. You're looking at an ever-increasing global demand for mobility, the proliferation of cloud-based systems, as well as big data analytics and the challenge that that brings to the table.
Sure.
To put some perspective here, for you, if you look at the chart that's up on the screen now, you're looking at memory interface bandwidth plotted as a function of time. And the thing that jumps out at you is that the application requirements seem to have memory bandwidth requirements that are doubling roughly every 2 years or so.
Yeah, it looks like that.
However, if you look at what the conventional memory technologies bring to the table, or for that matter, even general purpose IOs, they're only doubling every 4 to 5 years.
Yeah. So memory isn't quite tracking Moore's law now, is it?
That's exactly right. And as you can see from this chart, there is a gap.
Yeah.
The gap between what we have today and what next generation systems are actually demanding.
True, yeah.
To build on this, let's take a look at some projections. What you're looking at here is projections for a pretty large timeline from 2012 all the way to 2017 for a variety of end applications, consumer and business. As you can see, the plot here is essentially in exabytes.
Wait a second, exabytes? Manish?
That's a great question, Amelia. Exabytes is essentially, in mathematical terms, 6th power of 1,000.
Phew, okay.
Or, in other words, 10 raised to an exponent of 18. Building on that, in simple language, it's a quintillion bytes.
Whoa, okay.
Or simply put in human language, that's a humongous amount of data.
It is a humongous amount of data. Now, in particular, Manish, let's look at that consumer video block down at the bottom. Oh my goodness. People want to watch their videos, huh?
Absolutely. And as you can see, consumer video section in black, it takes the lion's share.
Yeah.
And if you sum it up all together, 2017, which is not so far off, takes you all the way up to 120 exabytes.
Wow.
So, well, the obvious question is, what do we do? Where do we go from here?
Sure, yeah.
And what the solution is. Well, it turns out, Amelia, that the solution is not a one-point solution after all. And the solution that is required to address this is a combination of some key factors.
Okay.
These key factors are bandwidth gains translated to performance gains.
Sure.
Power reduction in terms of energy efficiency per bit.
Makes sense.
Form factor reduction translates to board area reduction, as well as overall system level latency reduction. So clearly a tall order.
Yeah, absolutely. Okay, so we're here to talk about the hybrid memory cube. Now that we've discussed this enormous appetite of memory, what does HMC bring to the party?
Great question. The HMC is a revolutionary shift in the memory landscape today. And it promises to address all of the key metrics that we just talked about before.
Okay.
More specifically, it promises to bring increased bandwidth, much greater power efficiency, reduced system-level latency, and more importantly, it provides a solution which is smaller, scalable, and flexible.
Yeah.
So you put all that together, and you end up with a lower TCO, which is a total cost of ownership to you, the end consumer.
And everybody loves that. Okay, that sounds great, Manish, but how does the hybrid memory cube actually work?
Sure. So let's take a look at what the hybrid memory cube technology is all about after all.
Yeah.
Well, the hybrid memory cube technology is essentially a next generation 3D based multi-bank DRAM memory structure.
Okay.
That's quite a mouthful, isn't it?
It is.
So let's look at a picture. A picture is always worth 1,000 words. What you'll find there is the hybrid memory cube sitting up on the right-hand side on a standard PCB substrate talking to a host, which in this case happens to be an FPGA or an SoC.
Okay, and these are stacked die, correct?
That is exactly right. So the hybrid memory cube is essentially built up using 128 independent banks,
Okay.
more specifically DRAM banks, that are stacked one on top of the other using state-of-the-art 3D TSV technology, which stands for Through Silicon Via Technology.
Yeah, okay.
Now, it turns out that this entire stack of DRAMs is in turn sitting on a base logic layer.
Okay.
So you put all that together, and what you'll find is that the base logic layer performs a variety of very important controller functions. For example, credit-based flow control, CRC protection, automatic retry for failed transfers, just to name a few.
Yeah, okay.
In other words, it's doing some cool stuff.
Yeah.
Now, the memory space from the DRAM stack itself is actually divisible between the links or can be accessed as a single pool itself.
Okay.
Since you're talking about links, it's a good time to bring up the interface itself.
Perfect.
So the hybrid memory cube is built up using 4 links, and each link is constructed using 16 full duplex transceiver channels.
Okay.
Now, it turns out that each link can run at a variety of data rates, ranging from 10 gigabits per second all the way up to 15 gigabits per second per link.
Cool, okay.
Now, if you do the math,
Yeah.
that's 4 links built up using 16 transceiver channels, running at 15 gigabits per second per link, you end up with a big number.
Yeah.
And that number happens to be 1 terabits of raw aggregate interface bandwidth in each direction.
That's cool. Okay.
That's a huge leap from where we are today with conventional systems.
Absolutely.
Now, in addition to all of this good stuff, you also have advanced packet-based protocols that are employed by the hybrid memory cube technology, which greatly increase the efficiency of the packets going back and forth between the host and the memory itself.
Gotcha. Okay. So, what does the architecture of HMC actually look like?
Sure. The architecture of the hybrid memory cube technology, like I mentioned before, is built up using multiple DRAM layers that are
Okay.
stacked one on top of the other using 3D through silicon via technology. The DRAM layers, as you can see from the chart up on the screen, is in turn sitting on a common logic-based die. This logic-based die does a host of important controller functions that we talked about briefly before,
Yeah.
and in turn also has vault controllers. A vault, in this particular case, happens to be a collection of banks
Okay.
across all of the DRAM layers itself.
All right.
So if you take a little bit of a deeper look at the logic-based die itself,
Yeah.
what you'll find is a host of very advanced controller functions that are all inbuilt within the DRAM stack itself. If you look at the link interface controllers that are right here at the bottom of the logic-based die, these are built up using 16 full duplex transceiver channels, like we talked about before,
Yeah.
capable of running up to 15 gigabits per second in each direction. The crossbar switch, for example, enables multi-vault access per link,
Okay.
which essentially means that you can access any bank anywhere in the DRAM stack from any link.
Very cool. Okay.
There's a host of built-in self-test or BIST functionality built into the logic base layer, as well as advanced memory control and vault controller functions to make sure that you have a very efficient access to the DRAM from the external world itself.
Okay. So, Manish, can you show me an example of how we could use one of these in our systems?
Absolutely. So what you're looking at, Amelia, is a 400 gig system design example.
Whew. Okay. Let's go.
You have 400 gig ports connected to a network processor or a traffic manager,
All right.
which is doing a lot of important things such as table lookups, statistics, queue management, and so on and so forth.
Sure.
What you need to do is you need to buffer your packets as they are coming in from the line side over to the switch side and vice versa.
Yeah.
And you need to do so by maintaining 800 gigabits per second effective bandwidth as these packet transitions happen both from the ingress or the egress side.
Gotcha. Okay.
So that's the example that we're looking at here
Okay.
on this particular slide.
All right. Now, how does using an HMC in this application differ from what we would normally do otherwise?
So that's a great question. So let's take a look at it. We looked at a 400 gig system design example prior to this, and we also talked about the need for packet buffering and maintaining an 800 gigabits per second effective bandwidth.
Right.
Now, it turns out the hybrid memory cube does a phenomenal job of addressing the packet buffering requirements across a variety of areas.
Cool. Okay.
Let's take a look at these important areas one at a time. Start off with the most obvious, which is design simplification.
Yeah.
The benefit that HMC brings to the table is obvious from the graph,
Right. Yeah.
but I'll talk about it as well. You can get the job done with one HMC device versus having to employ up to 48 DDR4 DIMMs using conventional technology.
Wow.
That greatly simplifies the design flow process, as you can imagine.
Absolutely.
Second, let's talk about a reduced active pin requirement as well.
Okay.
Again, if you look at the plot here, you'll find that you can get the job done by deploying 4 15 gig short reach HMC links versus having to deploy up to 1900 DDR.
Right. Yeah. Okay.
So that's a huge advantage in itself, but it turns out that it has a secondary benefit as well, and a pretty important secondary benefit as a matter of fact.
Yeah.
And that turns out to greatly reduce the complexity of the board design as well, which in turn translates to lower bill of material cost
Sure.
that you, the end consumer, can directly take advantage of.
Absolutely. Yeah.
Smaller memory footprint, again, translates to board area reduction, reduced bill of material cost. The concept of abstract memory, which we talked about briefly in the previous slide, essentially the logic-based die, if you remember from our previous slide, which takes care of all the complex controller functions. Turns out this is really important because it reduces the system maintenance burden on the host.
Sure. Okay. Makes sense.
And finally, much better energy efficiency overall by being able to provide the solution at lower interface power in terms of picojoules per bit.
Yeah.
All in all, really cool stuff.
Absolutely. How far are you with this technology? Now, I do remember seeing an announcement about this recently.
You're exactly right, Amelia. This was a joint announcement between Altera and Micron that crossed the wire September 2013.
Oh, okay. Okay.
And this joint announcement talks about a successful interop between Altera's Stratix 5 FPGAs and the hybrid memory cube device. Now, it turns out this announcement is important for both entities for obvious reasons, but particularly for Altera, it's significant because it validates our technology leadership in the memory landscape. And secondly, and more importantly, it's an early proof point to be able to provide full production support for the hybrid memory cube technologies with our Generation 10 portfolio, which we'll talk about soon.
Ah, okay. Now, I see that EE Times screenshot there, Manish.
Oops.
Oh, yeah, okay. Now, tell me a little bit more about this interoperability part. Give me some details. I want specifics.
There we go. Let's talk specifics here, Amelia. What you're looking at is interop board itself.
Okay.
Over on the right-hand side, this has 4 Stratix 5 FPGAs.
Yeah.
And the hybrid memory cube device sitting up there, right in the center of it all.
Yeah.
There is one master FPGA on the board, and it's called the master primarily because it is able to talk to the internal configuration registers of the hybrid memory cube technology using the I2C sideband interface.
I see. Okay.
The hybrid memory cube device, which is sitting up right in the center of the board, has 4 separate full width by 16 full duplex transceiver links, like we talked about before. And the interop board itself has, like we talked about, I2C configuration capabilities of the HMC, as well as a host of advanced local power monitoring and control mechanisms as well.
Cool.
In terms of the configuration setup itself, we are exercising all 4 hybrid memory cube links independently. And we are exercising these links at data rates of 10 gigabits per second per link.
Okay.
We are using the full width configuration scheme, which effectively means that we are using 16 full duplex transceiver channels per link.
Okay.
We're also using a power of 2 payload scheme to transfer packets back and forth between the FPGA and the memory.
Gotcha.
To be specific, that means 16 bytes, 32 bytes, 64 bytes, all the way up to 128 bytes. So with the Stratix 5 interop solution, you have a validated solution that's available today. And customers can take advantage of this and start to plan deploying HMC for their next generation systems and take advantage of getting 15x more bandwidth, 70% less energy, and up to 90% less board area for their next generation systems.
Okay, so Manish, what kind of applications do you see this being adopted into?
So it turns out the solution here is very attractive to a host of end applications.
I can imagine.
Absolutely. Starting off, for example, with wireline communications, high performance computing, military, test, and measurement. For example, the wireline communication can greatly benefit from the pin efficient bandwidth, particularly for 400 gig systems that the solution would provide.
Sure.
Also benefit directly from the PCB densities directly as well.
Yeah.
And if you go down the list, you'll find the value propositions for each of these market segments clearly laid out.
Absolutely. Yeah, that looks good.
Key message here is that we are essentially enabling our end customers by providing this solution. And we are enabling them by essentially providing a higher performance and a lower power solution to be able to address the requirements across a host of end applications.
Very cool. Okay, so the example we saw was with Stratix 5, but you guys are introducing a whole new family of devices, right? Generation 10, is that right?
That is exactly right. So let's talk about Generation 10.
Sure.
The Generation 10 is essentially built up using 2 product families. The first one happens to be the Aria 10 product family, which is going to be built up using TSMC's 20 nanometer process and will feature 15% higher performance and up to 40% lower power compared to previous generations.
Oh, okay.
In addition to that, it has a 32-bit dual-core ARM A9 processor that's built into the fabric itself.
Okay.
Now, it turns out the last 2 bullets here are particularly important from the perspective of the hybrid memory cube technology itself.
Okay.
So let me talk a little bit about that.
Please do.
The Aria 10 brings up to 96 transceiver channels in all.
Wow.
And that's important if you are planning to use the hybrid memory cube technology, and particularly if you're planning to use 4 non-aggregated links together. Because if you remember, like we discussed, each link is built up using 16 full duplex transceiver channels.
Right.
And if you do the math, for 4 links, you end up with 64 channels that you would need.
Yeah.
With Aria 10, you will be able to do all the 4 links and have 32 transceiver channels left over to do any other important system function that your end application requires or demands.
Very cool.
So apart from the number of transceiver channels that has gone up significantly in Aria 10, the data rates at which these transceivers are running has also significantly gone up. As a matter of fact, the transceivers in Aria 10 can run 28 gigabits per second chip to chip. And that's important because as the hybrid memory cube specification moves on and progresses over a period of time, the Generation 10 portfolio will have more than enough ammo to be able to provide a powerful and effective solution.
Mm-hmm.
Over on the right-hand side, we have the Stratix 10, which is really our next generation ultra high performance device.
Mm-hmm.
The Stratix 10 is going to be built using Intel's state-of-the-art 14 nanometer Tri-Gate process. And the combination of process and architecture is going to bring in 2x performance increase, or up to 70% lower power compared to previous generation.
Wow, okay.
That's a significant leap
Yeah.
in the FPGA domain. In addition, the Stratix 10 is going to have a 64-bit quad-core ARM A53 processor built into it,
Okay.
and will also feature 3D-capable devices, which will enable heterogeneous integration of either SRAMs, DRAMs, or ASICs down the road.
Very cool.
In addition to all of that cool stuff, you also have way more transceiver channels and even higher transceiver data rates to be able to address the HMC requirements downstream.
Very cool. Okay.
So all in all, with the Stratix 5 interop today, Altera has a proven solution that has been validated today. In fact, has been demonstrated in important industry conferences. For example, the Supercomputing 13 that just concluded in November, we demonstrated the Stratix 5 interop solution very successfully.
Mm-hmm.
The Generation 10, the one that we just looked at, essentially combines state-of-the-art performance and power advantages to provide full volume production for the hybrid memory cube device.
Okay. Well, I think that's all I have time for. Thank you so much for joining me today, Manish.
Thank you, Amelia. It's great to be here.
Also, before we go, remember to click that link. There you can download a free white paper entitled Addressing Next Generation Memory Requirements with Hybrid Memory Cube Technology. For Chalk Talks, I'm Amelia Dalton. For more Chalk Talks, check out the on-demand section of eejournal.com or EE Journal's YouTube channel.